Hi everyone. Today we're going to be talking about acceleration. What is acceleration? It's defined as the rate at which an object's velocity changes. What does it mean to change your velocity? Well, that just means getting faster or slower. So acceleration is a measurement of how quickly you're changing your speed, either to speed up or to slow down. Let's look at this animation playing in the corner. You can see four shapes that are all rolling down the same ramp, and some of them have a greater acceleration than others. For example, the yellow sphere has the greatest acceleration because it changes from no velocity to lots of velocity the quickest out of the four. The green hollow circle, on the other hand, has the lowest acceleration because it changes its velocity over a longer period of time. Now, rather than just looking at acceleration with things rolling down a ramp, let's look at where you might see acceleration practically in the real world, and that is when you're driving a car. So I'm going to open up this simulation from a site called Physics Aviary. And in this simulation, I'll be able to control a car as it accelerates, travels at a constant velocity, or decelerates. I'm going to start the simulation, and you'll see a car moving forward at a constant velocity of, it looks like, about 11 meters per second. Now, I'm not hitting any of the gas pedals or brakes or anything. It's just going at the same speed all the time. But if I press down on the accelerator, it accelerates, which makes sense, and that's why it's called the accelerator. If I let go of this pedal, it now maintains the same constant speed that I just gave it. Now, sometimes in the real world, cars will grind to a slower speed when you're not pressing the pedal, and that's because of friction. Friction isn't being represented in this animation here. So now what I have is a completed velocity time graph, and that blue line represents how fast the car was moving at any given point. You can see that it was traveling slower at the beginning, then I accelerated in the middle, and then I had a final speed that was faster at the end. I'm going to reset the simulation, and I'm going to start it again, and this time I'm going to hit the accelerator early on, so that we can accelerate faster and faster and faster, and you'll be able to see the car in the animation is going really fast now. Then I'll let off the accelerator, and you can see that it's now traveling at a constant velocity. I'll hit the brake, and the brake is to decelerate the car. As you hopefully know, those of you who are getting your license, this is an essential pedal to be familiar with. So this VT graph shows the car going much farther than the original one does because it was traveling at higher velocities for most of the time in this graph compared to the last one. So the displacement of this car was greater this time around. So what can you do with a graph like this? Well, as we'll see, you can use a VT graph like the one we've just made, even if you weren't actually there for the graph's creation, to figure out what was the acceleration of that car. How quickly was it able to speed up, and how quickly was it able to slow down? So let's return to the presentation, and let's look at the formula for acceleration. The equation that we're going to use this year to represent how quickly something is changing its speed, or what is the acceleration, is this formula. It starts with these two ideas. You have to know first what the final velocity of the object is that is doing the acceleration, and then you have to subtract from that what its original or initial velocity was. Once you have those two things, you're going to divide that answer by this calculation, the final time period after the acceleration was ended, minus the original time when the acceleration began. So there's four things in here, and these words are all pretty long when you string them all together like this. Most equations in physics we like to shorten so they're easier and quicker to write. So here's the shortened version of the acceleration formula. And it says, the acceleration of an object is equal to final velocity minus initial velocity divided by final time minus initial time. Sometimes this formula is shortened even farther to look like this, which is a little less common, but you'll see on some websites and resources. And that's because there's a Greek symbol that is being used here that isn't always common in introductory physics classes, but we use it sometimes here. That little triangle symbol is the Greek symbol delta, and what it means anytime you see it is the change in something, how much increase or decrease we had of that thing. So in this formula, it says the acceleration of an object is equal to the change in velocity divided by the change in time. Delta V divided by delta T. So let's see an example of this calculation being used, or this formula being used rather. In this animation over here, we have an object, a ball that's being dropped, and that ball is being dropped from an original time of 0 seconds, because we're going to start the timer when the ball starts dropping, so it'll be at 0 at the beginning. And when you drop an object, you may know that objects don't originally have any speed at the moment you drop them, so its initial velocity will be 0. But after we give it some time, let's say half a second to fall, it will have gained some speed because gravity is going to accelerate it towards the center of our planet. So the final velocity could be something like 5 meters per second. So let's put these four measurements into our acceleration formula, and let's find out what the acceleration of this ball is. Given these numbers, we can take the final velocity and subtract the initial velocity, so that's 5 minus 0, and we can divide that by the final time minus the initial time, which is 0.5 minus 0. The zeros make it pretty easy in this case, but eventually those initial properties won't always be 0. Our answer comes out to 10. And the unit I'm using to describe how much acceleration that ball has is meters per second squared. So what's the deal with that? Well, we have to learn the unit for acceleration. Nearly every measurement in physics has a unit of measurement, and the base unit of measurement for acceleration is actually a combination of two other units. It's a combination of the meter per second, which is the unit for velocities, and seconds, which is the unit for time. So that kind of makes sense that the units come from the things that are in the formula. Now, meters per second doesn't necessarily roll off the tongue very well. You want something shorter and quicker and punchier to say when you're describing how much acceleration something has. So if you combine all these words, you can shorten it to meters per second squared. This kind of makes sense because acceleration is how quickly you're gaining or losing meters per second of speed. So it's meters per second. And because the per second is in there twice, we just combine those into a seconds squared. So that's the formula for acceleration, and now if you were ever given a physics problem with these 4 bits of info, you could calculate the acceleration. But you are going to also need to figure out the acceleration of an object when you're not presented with numbers, but instead a graph. So we're going to take another look at VT graphs and DT graphs and figure out if there's a trick or some kind of way where we can figure out how much acceleration an object has from a graph alone. So you probably remember these graphs. These were from the story of Paco the squirrel, who was being chased by an eagle and trying to get an acorn and all this cool stuff. And the VT graph that we came up with, that's the blue one on the bottom, described his velocity as time goes on. Now you might notice that he was traveling at 2 meters per second at first and then suddenly was traveling at 0 meters per second. And that's a pretty sudden change of velocity. And in truth, it is true that you can take a DT graph and use the slope of those lines to make the VT graph. So these graphs are made correctly, but the graph that you're looking at here is not representing what I'd call realistic motion. Because realistically, even a squirrel who's very, spry and able to move very quickly is not going to be able to instantaneously change its velocity. What's more realistic is if graphs are curved or sloped, so that you can show that things gradually speed up and gradually slow down. So I'm going to show you some animations here that represent slightly more realistic speeds and accelerations. So there's going to be an animation on the top here that shows an object that is starting out from rest and then accelerating to a high velocity. And then it also shows the DT graph on the left and the VT graph on the right that represent this motion. The DT graph is curved because it shows that the object is getting faster and faster and faster, so the slope of that graph keeps getting higher and higher and higher. And the VT graph, which operates on different rules, this is a straight line. And that's because this graph says how fast it's going, and if you look at the motion, as time goes on, it does get faster and faster and faster, so a fastness graph, which is what the VT graph is, that should be getting higher and higher and higher at a consistent rate. So if you wanted to describe this object, you could say that it has a constant positive acceleration. Constant because, according to the velocity time graph, it's always gaining a consistent amount of speed each second. Positive because it's getting faster in the positive direction. And acceleration because its speed is changing. How can you recognize constant positive acceleration? Well, on a DT graph, constant positive acceleration will look like a curve bending upward. And on a VT graph, it will look like a straight upward line. So this is an example of acceleration where an object gets faster and faster and faster. What about the opposite? What about deceleration? Well, you probably know deceleration is when an object slows down. So in this second animation here, it shows an object that's originally traveling at a fast velocity, but then gets slower and eventually comes to rest. So what does the DT and VT graph look like in this case? Well, the DT graph starts out with a high slope because it's going fast, but then it kind of peters out and flattens to show that the speed has now gone to 0. And the velocity time graph, which again uses different rules than the DT graph, is representing how fast the object is going as time goes on. So it originally shows that it's going pretty fast, and then later it goes down to 0 speed. So there's that line going consistently down. So again, the rules for these graphs are different. This would be an object that has a constant negative acceleration. What does it mean to have negative acceleration? Well, that means that it's accelerating in the negative direction. That is, if it's going forward, that means it's slowing down. And if it's going backwards, that means it's getting more backward speed as time goes on. So it's tending towards the negative direction more and more and more. So how can you recognize constant negative acceleration on a VT graph or a DT graph? Well, on the DT graph, which is the one on the left, you'll notice a curve, and in this case it's bending downward. And on a VT graph, it will be a straight line pointed downward. And again, the graphs represent the same motion, but they're using different rules, so they represent that motion in different ways. The graphs on the left show where the object is. The graphs on the right show how fast it's going. That's why they look different. So let's check out a VT graph that might look like the ones you'll have in class so that you know how to analyze them properly. This is going to be the story of Peanut the puppy. And Peanut the puppy one day was sitting in his backyard at rest, which means not moving, or 0 meters per second of velocity, when his owner threw a ball. And so he started to run forward after the ball and gained some speed. Then he started sprinting as fast as he possibly could. Then he approached the ball, and so he started slowing down so he could pick it up. And then he picked up the ball. And when he was picking it up, of course, he was no longer running, so at that point his speed had become 0 meters per second again. Once he had gotten the ball, he needed to return to his owner, so he started traveling backwards, or in the negative direction, and he starts trotting, and then he breaks into a full sprint going backwards towards his owner. Then as he approaches his owner, he slows down and stops to hand his owner the ball because he's a very good boy. Yes, he is. And then the owner gives him a pat on the head, and then Peanut the puppy sees his neighbor's dog and gets really excited and runs back across the yard to go say hi, runs into a full sprint. So that's the story of Peanut the puppy. And a question you could ask about a VT graph like this, and notice that this is a VT graph, it's not a DT graph. This graph did not describe where he was, it describes how fast he was moving. And you can see from the little pictures which direction he was facing as a helpful guide. So a question you could ask about this graph is, what was Peanut's acceleration for all the different parts of this graph? His acceleration isn't just going to be one value, it's something that could change as time goes on, so we'd have to look at each section of the graph separately to answer this question. But first, what strategy are we going to use to answer the question? Well, we have one equation that we can use to calculate Peanut's acceleration, and that is, what was Peanut's change in velocity, and what was the amount of time it took for him to change that velocity. We could plug those numbers into a formula. And a shortcut to doing that, so that we don't have to work with the formula as often, is to consider this little trick here. The slope of a VT graph actually does this calculation for you and tells you what the acceleration of the object is. So remember that slope is just rise over run. So let's calculate the rise over run for this graph of Peanut the puppy. Let's figure out what his acceleration was in each part. So in the first section, his acceleration would be 1.5 meters per second squared. How did I get that number? Well, it's because I'm looking at the slope, and the slope of this first section would be a rise of 3 divided by a run of 2, because these first two blocks represent 2 seconds. So rise over run, 3 divided by 2, gives me 1.5. What about the next section? Well, that would be 0 meters per second squared, because the rise is 0 in this section. He doesn't go faster or slower. He has no acceleration. He stays the same constant speed during this part of the journey. What about the next part? Well, that would be negative 3 meters per second squared of acceleration. Actually, this would be a deceleration at first. So how can you tell he's decelerating? Well, first, you can see that his velocity starts out at 3 and then ends up at 0, and then keeps moving towards negative 3. So his velocity is going down, down, down. And it takes 2 seconds for this whole part of the journey to occur here. So it goes from 4 seconds to 6 seconds. So again, 2 seconds. And the rise, in this case, is negative 6. So where do I get negative 6 from? Well, he started at 3 meters per second of velocity, and he ended at negative 3. So if you start at 3 and you end at negative 3, that's a change of negative 6. So the rise was negative 6, the run was 2, rise over run is negative 6 divided by 2 is negative 3 meters per second. This section right here was 0 acceleration because he's staying at a constant speed. You could also say there's no rise to put over the run here, so there's no slope. It's a slope of 0. So the slope of a VT graph tells us acceleration. If there's no slope, there's no acceleration. The next part is positive 3. And if you were paying attention, you might have predicted that even without doing any numerical analysis, because this section of the graph has exactly the same slope as this section of the graph, only this one is oriented upwards, whereas this one's oriented downwards. So it's exactly the same amount of acceleration, but it's positive acceleration instead of negative acceleration. So this means he's going backwards at first, but then he keeps tending towards going forwards this entire time at the same consistent rate. And that rate is 3 meters per second of speed gained every second. And finally, the last part, he is at, again, no acceleration. And that's because he's not gaining any speed as time goes on. He's staying at the same consistent speed the whole time. So that was how you use a VT graph in order to calculate the acceleration of an object. And again, what does acceleration mean? It means the rate at which you are gaining or losing velocity over time. So I hope this was helpful, and I'll see you in the next video.